Hello everyone. In this work I focus on multi-chip quantum systems, exploring how improvements in the classical communication infrastructure can enhance the overall performance. This work is partially funded by European Commission through the Pathfinder Quadrature project. Current quantum computing systems are monolithic systems comprising a few hundreds of qubits, and this number is very small to tackle real-world application. The main problems which affect the scalability limitation includes wiring congestion, reduced fabrication yield, increased crosstalk, etc. The promising architectural direction is the multi-chip quantum architecture, in which the quantum processor is partitioned into multiple quantum cores and connected by means of a classical and quantum coherent network. Each quantum core integrates a manageable number of qubits alongside its local control electronics and thus alleviating wiring density and fabrication yield issues. In the last year edition of MCSoC, we proposed a multi-core quantum system as shown in this figure. The proposed architecture is formed by a memory that stores program instruction, global control units that fetches the codes and dispatches instruction bundles, an EPR generator for creating and distributing entangled pairs to support the teleportation protocol, an array of quantum cores that executes the quantum gates, and a communication system which is composed by a quantum and a classical plane. Each quantum core integrates a set of physical qubits, one or more light-to-matter ports, and a local controller. LTM ports enable interaction with remote quantum cores through photonic channels by using dedicated communication qubits. The local controller interprets instructions received from the global control units and drives the execution of local operations. Here is an example of the compilation flow. Operations that involve qubits belonging to different quantum cores like the CNOT gate between Q1 and Q2 are transformed into a teleportation-based instruction. The resulting assembly codes consist of instruction bundles, each grouping operations that can be executed in parallel. In this example, we see two special instructions which are introduced, TPS and for the source quantum core, handling the generation, distribution, and measurements phases of the teleportation protocol, and a TPD for the destination quantum core, which performs the final correction based on the received classical bits. Classical communication among the control units and quantum cores is realized by means of a wireless network on a chip. Here is an example of the execution of a bundle containing the TPS and TPD instruction. First, the control unit fetches the instruction bundle which implements the teleportation operation, aiming to teleport the quantum states of qubits C to F. Then the TPS instruction is dispatched to the quantum core 1 and TPD instruction is sent to quantum core 2. Simultaneously, the EPR control module configures the EPR generator. Then the EPR pair is distributed to both QC1 and QC2. Then the local control units of QC1 executes the preprocessing phase of the teleportation protocol and transmits the 2-bit classical information to QC2. The control unit of QC2 then performs the post-processing phase to complete the teleportation. Finally, QC2 sends an execution complete message to the control unit. All the red arrows correspond to data transfer, which are implemented through the wireless network on chip. In a wireless NOC, the medium access control protocol plays a key role. Traditional MAC schemes is based on a token-controlled medium access in which a control packet, which is called token, is circulated among the nodes. At any given time, only the node holding the token is permitted to transmit. After completing its transmission, the token is released and forwarded to the next node. This approach presents several drawbacks, as its performance is highly dependent on the token circulation latency and the spatial distribution of the traffic. Thus, we propose the instruction-directed MAC protocol, which is based on the observation that after compilation, the complete communication schedule of the quantum circuit is known in advance. In particular, the compiler identifies all the teleportation operations and determines the corresponding transmission events between quantum cores. This knowledge allows embedding into the instruction information that specifies whether a quantum core must access the wireless medium during the execution of that instruction, and if so, in which order relative to the other participating quantum cores. Thus, the token circulates among the only nodes that have something to transmit. To support the instruction-directed MAC, several packets formats are defined. I don't want to enter into the details that can be found in the paper, but the only thing that I'd like to comment is showing that some of the packets, like that used to dispatch the TPS instruction, includes token order fields, which specify the sequence in which the corresponding teleportation operation is permitted to access the wireless medium. Let me very briefly present some of the processes that implement the protocol. During the dispatch phase, the dispatch process is executed by the global dispatcher. It receives an instruction bundle, generates the corresponding instruction packets, and transmits them sequentially to the quantum cores involved. In the same dispatch phase, each quantum core executes a buffer fill-up process, which receives instruction packets and stores them into the appropriate buffer. In the execution phase, each quantum core runs for 4 concurrent processes. The local instruction process fetches and executes instruction from the local instruction buffer. The TPS instruction process manages TPS instructions. Specifically, it waits for the token corresponding to the token order value stored in the TPS instruction. Then, after executing the instruction, the correction bits are transmitted to the destination quantum core. Then the token order is incremented and the token packet is generated and transmitted. The TPD instruction process executes the post-processing phase of the teleportation. It waits for the arrival of the correction bits and executes the post-processing parts of the teleportation protocol. Finally, the end of computation process monitors the completion of all the local operation, and once all the buffers are empty, it sends an end of computation packets to the control unit. We implemented the ID-MAC protocol into the QCOM simulator and performed a set of experiments considering the simulation parameters and configuration details which are summarized in this table. We first evaluate the impact of the classical communication subsystem of the overall execution time. In particular, this graph shows the breakdown of the execution time under randomly generated quantum circuits whose size scales with the number of quantum cores. And as can be observed, the contribution of the classical communication, which is the green segment in the bar, becomes increasingly significant as the number of quantum cores grows. To further explore these trends, we analyze how improvements in quantum technology affect the importance of classical communication. So we defined a quantum scale factor, QSF, which scales all quantum-related delays by a constant factor, and this is to emulate the technology advancement. The graph shows the fraction of execution time devoted to classical communication for varying numbers of quantum cores and QSF values. As it can be observed, as the QSF decreases, which represents faster quantum operation, the fraction of time spent in classical communication increases. That is, as quantum technologies evolves and quantum operation becomes faster, the latency gap between the quantum and classical components narrow, and eventually making classical communication a dominant performance bottleneck. This graph compares the proposed instruction-directed MAC protocol with the baseline circulated token MAC. The analysis considers varying number of quantum cores and QSFs. And for each configuration we measure the fraction of total execution time spent to classical communication and the overall reduction in execution time achieved by IDMAC. As it can be observed, IDMAC achieves a substantial reduction in the time spent on classical communication compared to that found for the CTMAC. The improvement becomes more and more relevant as the system scales. Finally, this graph reports the comparison between CTMAC and IDMAC for real benchmark. Although the overall system size limits the absolute contribution of the communication to total execution time, IDMAC still provides improvement. Specifically, the proposed protocol nearly eliminates classical communication delay, yielding total execution time reduction. In conclusion, we showed that classical communication plays an important role in this multi-chip quantum system. We exploit the deterministic execution flow of quantum circuits to guide token circulation dynamically, and we proposed a new MAC protocol for wireless network on chip in this context, called IDMAC. That's based on our experiments. We show that we can reduce the classical communication time by up to 70%, the overall execution time from 30 to 70%. Future work are mainly devoted toward the extension of the protocol to support multi-token operations. Thank you very much for the attention.